After main engine ignition, there's no way to stop a rocket if something goes wrong during flight. Rocket launch abort systems are a sort of insurance plan. What if the engine cooling jacket fails and the combustion chamber melts through? You'll want to eject the crew capsule away from danger. In this video, we'll explain why rocket launch systems work and how they've been continuously developed since the 50s. Before we begin, don't forget to subscribe to 26 Dimensions. We're going to be posting weekly videos about space exploration and astronautical engineering, and you won't want to miss them. Since the 60s, the thinking behind launch abort systems was that if you used a set of smaller boosters attached above the manned capsule, you could effectively pull the spacecraft away from the rocket body in an emergency. Both the Mercury and Apollo launches utilized rocket-powered getaway towers that could pull the capsule away in the event of an engine meltdown, a fuel tank instability, or other malfunction. This getaway tower was a strong fuel rocket and sat atop the payload container. It had enough fuel to pull the capsule far enough from the rocket to enact a conventional parachute landing. On the Gemini missions, however, discharge seats were used for the two crew members to get away from a dispatch failure. The rocket-fueled seat would force the space-going chimp out of the capsule and away from the malfunctioning boosters. At that point, the astronauts would eject from the craft and attempt a normal parachute landing. Luckily, no Gemini launches ever fizzled, and the launch seats and parachutes were never used on a genuine space launch. From an engineering perspective, the exact configuration for a launch abort system depends on various design and practicality aspects. An abort system needed to provide a reliable and secure abort which could be easily incorporated into the rocket payload module. On the early Soviet Soyuz rockets, the SAS system would include an engine framework attached to the head of the payload fairings, capable of delivering a force of 4 tons to pull the capsule from the rocket. The system would be calibrated to the rocket's point of gravity and launch trajectory, so the capsule could be directed along the correct route to avoid danger. On the off chance that the rocket strayed from its intended path and chased down the ejected capsule, the flight direction of the module could be corrected by controlling the angle of the solid fuel rocket nozzles. On the first Soyuz shuttle, the getaway system was engaged 15 minutes before launch and could be used up to the 157th second into the flight. The primary getaway engines would fire for 2 to 6 seconds, accelerating the home module and reemergence container up to 150 meters per second. The getaway capsule would reach an altitude of 1.5 kilometers before it could attempt a parachute landing. After the ejected craft had escaped immediate danger, the reemergence case would be detached from the fairings and a small division engine would fire to shoot the container away. The manned reemergence container would then deploy its parachutes and splash down. This conventional method is effective and reliable, but it is not efficient. For one thing, the bulky escape pinnacle overloads the capsule. What's more, the engines and fuel usually end up being dumped into the sea. So engineers set to designing better approaches to whisk space explorers away from dangerous rockets. The most recent methodology is to drive the capsule away, rather than pull it. In 2010, Boeing demonstrated the concept at the Farnborough Air Show. Furthermore, SpaceX has taken that concept and is creating their own similar abort system. It even sold NASA on their plan, and the agency signed a $75 million deal with SpaceX to develop what they call a progressive dispatch getaway framework as part of the Commercial Crew Development Program. SpaceX's methodology contrasts Boeing's in that it incorporates brake motors into the side dividers of its Dragon capsule. The side-mounted rockets will fire downwards if a crisis occurs. SpaceX proclaimed in what was to some degree a horn-honking declaration that their framework would allow the crew to escape at any point in the flight, not just the ascent, but also the orbital injection maneuver. The Dragon capsule's brake engines could also give the shuttle the ability to land any place on Earth or another planet with high accuracy. In January this year, the Dragon capsule performed a successful escape maneuver rehearsal, and the craft was able to eject away from the rocket using its escape engines and avoid a pre-planned explosion of the rocket's fuel tanks. It splashed down in the sea and was retrieved without any issue. Elon Musk's vision to turn the Dragon capsule into a versatile Earth to space and back again shuttle for a range of missions is a big step forward from the days of NASA's Space Shuttle, which didn't even have any escape function. STS Challenger's crew were therefore unable to perform a getaway move when the rocket exploded and consequently died on impact with the sea. Escape frameworks have been designed for virtually all other endeavors into space, and the process of engineering a reliable getaway module has always been a major priority for space agencies around the world. With modern technology, it's highly likely that we'll see a great deal of innovation in abort systems in the coming years. In this video, we looked at the reasoning behind rocket abort systems, the typical setup of a getaway module, and what plans there are for the future of this field of engineering. If you enjoyed the video, please consider subscribing to 26 Dimensions. I'm putting out weekly space exploration videos, so if that sort of thing interests you, you'll want to be notified whenever I upload another video. I'm working on a step-by-step guide for getting a human into orbit next. Stay tuned for it. Thanks for watching, and I'll see you next time.